there are 18 vertical columns. Okay, you go through the periodic table again. See, in the modern periodic table, say there are 18 vertical columns. See, you can see from left to right. You take the main block of the periodic table. The main block of the periodic table. In the main table, there are 18 vertical columns. Say from left to right. They are named as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. So 18 vertical columns. And these 18 vertical columns are known as 18 groups. Sometimes they are known as families also. 18 groups or 18 families. Now we are going to divide the periodic table into, say, 4 blocks of elements. 4 blocks. You come to the left end of the periodic table. See, the left end, you take these 2 groups. That is, these 2. Group 1 and group 2. Group 1 and group 2. In these groups, group 1 and group 2, while you write the electronic configuration, the last electron enters an S level. And therefore, these are called the S block elements. These are the S block elements. Now you come to the right side. You take, say, these 6 groups of elements. That is 13 to 18, 6 groups. 13, 14, 13, 14, 15, 16, 17, and 18. In these 6 groups, while you write the electronic configuration, the last electron enters a P level. And therefore, these are called the P block elements. So these are the P block elements. In the P block, while writing the electronic configuration, the last electron enters a P level. In the S block, when we write the electronic configuration, the last electron enters an S level. All right. Then you come to the middle portion of the main table. See, here there are 10 groups, 10 vertical columns, starting from group 3, 4, 5, 6, 7, 8, say 9, 10, 11, 12. So there will be 10 vertical columns or 10 groups. And these elements are called the D block elements. The middle portion, D block elements. Why is it known so? The reason is this. When we write the electronic configurations of these elements, the last electron enters a D level. Say when you write 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 3d 1 to 10, 3d 1, 2, 3, 4, 5, etc. up to 10. The maximum capacity of the D level or a D subshell that we know, it is 10. So there are the D block elements at the middle of the table. Now all the main groups, 18 groups are over. Now you come to the bottom of the main table. Say at the bottom of the main table there are 2 rows. Each row consists of 14 elements. Each row consists of 14 elements. And in these elements, the last electron enters F level. Last electron enters F level. And therefore, these elements are called F block elements. So in the F block elements, the last electron enters an F level corresponding to 4F and 5F. 4F and 5F. We have two F block series, and they are called lanthanide series, and the second one is called the actinide series. The lanthanide series consists of the elements coming after lanthanum. Say, the elements coming after lanthanum from here, coming after lanthanum. And these are the elements cerium to cerium, say this one, 58 cerium, cerium to 71 lutetium, 14 elements. In the table, you can see, say, lanthanum also, along with these 14 elements. But because, say, the properties of the element lanthanum are found to be similar to the properties of the following elements. And therefore, lanthanum is also incorporated along with lanthanoids or lanthanides. Actually, lanthanum is seen here. It is here, lanthanum 57. And the other elements will be coming after lanthanum. They are called the lanthanoids. But usually, lanthanum is also incorporated along with the lanthanoids due to the similarities and properties of lanthanum. Similarly, you come to the elements coming after actinium. Actinium, see, this should be here in the third group. But after actinium, there are 14 elements. And these are the elements of thorium 90 to 103 lawrencium. Thorium 90 to lawrencium 103, 14 elements. And in these elements, the last electron enters 5F level. So the elements corresponding to the filling up of the 4F level are called lanthanoids. The elements in which the last electron enters 5F level are known as actinoid elements. So there are 4 blocks of elements. Okay. One thing more you must bear in mind. You come to the horizontal rows. Say horizontal rows 1, 2, 3, 4, 5, 6, 7. There are 7 horizontal rows and they are known as periods. Say 7 periods. Period 1, period 2, period 1, period 1, period 2, period 3, 4, 5, 6, and 7. These are the 7 periods, the horizontal rows. In the first period, say, in the first period, there are only 2 elements, say hydrogen and helium, only 2 elements in the first period. In the second and third periods, say, for example, second period, this one, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. There are 8 elements. Some gaps are there between S and the P blocks. Some gaps are there. Okay. So 8 elements. Similarly, in the third period also, there are 8 elements. So in the first period, only 2 elements. Second period, 8 elements. Third period, also 8 elements. Then you come to the fourth and the fifth. Fourth and fifth. Say fourth one, this one. Say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. There are 18 elements. In the fourth period, there are 18 elements. 18 elements. Similarly, you come to the fifth period. There are 18 elements. Say 1, 2. Okay, you come to this. The elements are, see, the elements are, 18 elements are from rubidium to, say, it is ending with the xenon, 18 elements. So first period 2 elements, second period 8, third period 8, fourth 18, fifth 18. Now you come to 6 and 7. In the sixth period, there should be 32 elements, 32 elements. But we have only 18 columns, 18 columns. So there should be provision for 14 more elements, and they are the lanthanoid elements. Lanthanoid elements. Similarly, in the seventh period also, 32 elements are possible, but we have only 18 columns. So there should be provision for 14 elements, and they are the actinoid elements. They are kept below the main table as two separate rows. Okay. Let me ask you to remember one more thing. See the position of hydrogen. Position of hydrogen. Hydrogen is seen at the left end of the table, but hydrogen is not included along with the remaining elements of group 1. In group 1, lithium, sodium, potassium, rubidium, cesium, francium. These are the elements. Hydrogen is not added to the remaining elements of group 1 because hydrogen has a special position that is kept always in a separate box. It is kept in a separate box. That is due to the peculiar property of hydrogen. The remaining elements of group 1, lithium, sodium, potassium, rubidium, cesium, and francium, these elements are known as alkali metals. So these are called group 1. They are called alkali metals. They are called alkali metals. See, they are called alkali metals. The group 1 elements are called the alkali metals. Now you go to what is going on? Okay, so in the first period, as you have seen, 2 elements, but hydrogen is kept in a separate position, in a separate box. Only the other elements are grouped together, and they are known as the alkali metals, lithium, sodium, potassium, etc. Group 17 elements, they are called the halogens, fluorine, chlorine, bromine, iodine, etc. And the last one, that is the noble gases, 18th group, they are the noble gases. All right. Now let us see the periodic trends in the periodic table, modern periodic table. What are the periodic trends? The periodic trends. First, let us see the atomic radius. The atomic radius. Atomic radius. You know, it is the size of the atom. It is the size of the atom. As we know, there is the central core, that is the nucleus of the atom. Protons and neutrons are present in the nucleus, and electrons are revolving around the nucleus in various orbits. Now you take the radius of this orbit, that is the distance between the nucleus and the outermost shell, the radius of the circular orbit, the distance between the nucleus and the outermost shell. That is called the atomic radius. But we cannot easily measure the atomic radius. So what we do? You take two, say, atoms joined by a covalent bond. Here there is a covalent bond. Now you take half of the distance between these two nuclei, half of the distance between the nuclei, and it is taken as the atomic radius. It is known as the atomic radius. Okay, so you need not think of this too much. Okay, so the atomic radius is the radius of an atom. You remember in that way, radius of an atom. Atom is considered as a sphere or something like that. The outermost level is always S. So we can consider it as a sphere. Now you take the radius of the sphere, and that is called the atomic size or atomic radius. Let us see the variation of the atomic radius. From left to right, what happens to the atomic radius? From left to right in a period from left to right, atomic radius decreases. Atomic radius decreases from left to right. Atomic radius decreases. Why is it so? That is because the electrons are added into the same shell, into the same outermost shell, but the nuclear charge, atomic number increases, nuclear charge increases, atomic number increases, nuclear charge increases, and therefore the attraction between the nucleus and the outermost shell increases, and therefore the atomic size decreases. From left to right, atomic size decreases along a period from left to right. That is because from left to right, atomic number increases, nuclear charge also increases, but electrons are added into the same valence shell, outermost shell. So the attraction between the outermost shell and the nucleus increases from left to right, and therefore the atomic size decreases from left to right. But you take the case of the variation from top to bottom in a group, in a family. In a family, down the group, new shells are opened. New shells begin. In the first period, there is only one shell. Second period, there are two shells. Third period, there are three shells. Fourth period, there are four shells. Fifth period, there are five shells. Sixth, there are six shells. Seventh, there are seven shells. So down the group, the number of the shells increases, and therefore the attraction between the nucleus and the outermost shell decreases. New shells are opened, and therefore the size increases. Down the group, the atomic size increases. Down the group, the atomic radius or atomic size increases from top to bottom. In a group, from top to bottom, atomic size or atomic radius increases. This is because down the group, new shells are opened. As I told, in the first period, there is only one shell. Second period, two shells. So new shell is begun. Similarly, seventh period, there are seven shells. So the number of shells increases down the group, and therefore the atomic size or atomic radius increases down the group. All right. Now you come back to the period again. See, in a period, I told you from left to right, the atomic size or atomic radius decreases. But you consider the size of the noble gas atoms. The noble gas atoms are at the right end of the period. The noble gas atoms are at the right end of the period. They have completely filled shells. They have completely filled shells, valence shells. And there is, say, inter-electronic repulsion, more inter-electronic repulsion between the electrons in the outermost shell, and therefore there is an expansion for the shell, and therefore the size increases. In general, we say the atomic radius decreases from left to right along a period. And this trend can be seen from, say, group 1 to group 17. That is the halogens, only up to that. The 18th group, again, the size increases. In the 18th group, there are the noble gas atoms. And in the noble gas atoms, there is a, say, large resultant inter-electronic repulsion within the shell. Within the shell, there is mutual repulsion between the electrons in the shell. And due to the repulsion between the electrons in the shell, there is an expansion for the shell, and therefore atomic size of the noble gases increases. Noble gases increases. So the general trend, that is decrease in the atomic radius from left to right, that is seen only up to 17th group, that is halogens. Only up to halogens. In the 18th group, again, the size increases. So there is an abnormality in the size of the noble gas atoms, the radius of the noble gas atoms. Okay, so that's about the variation of Anthony, Atul, Emmanuel, Evelyn. Say, what is the variation of atomic radius along a period? Atul, variation.
From group 1 to 17.
From left to right, in general, from left to right, in general, the atomic radius decreases. And that is seen only up to the 17th group. That is halogens, fluorine, chlorine, bromine, iodine, etc. And the last group, 18th group, still the size increases. And that is due to the mutual repulsion between the electrons within the shell. Okay, from down the group from top to bottom, as you know, the principal quantum number increases. Principal quantum number increases down the group. First period, n is equal to 1, only one shell, n is equal to 1. Second period, n is equal to 2 shells. Then third period, n is equal to 3. Fourth period, n is equal to 4. So the principal quantum number increases, the number of cells increases, and therefore down the group atomic size increases in general. So that is the variation of atomic radius. Variation of atomic radius along a period, and say along a group also. We have seen this. Now you come to the ionic size of the ions, ionic size or ionic radius. Ionic size or ionic radius. So let us see what happens to the ionic size or ionic radius. What happens? Let us think of the size of or a radius of a cation and a parent atom. A cation and a parent atom. See, your example, you take an atom A. From this, one electron is removed. Minus 1 electron. An electron is removed from atom A. Then you will get A plus ion. A positive ion is formed. A positive ion is called a cation. So cation or positive ion is formed by the removal of electron, the loss of electron from an atom. Say for example, take sodium. Sodium, atomic number is equal to 11. 11. And the electronic configuration will be 1s2, 2s2, 2p6, then 3s1. That is the configuration. 11, atomic number 11, and there are 11 electrons. So, in the K shell, there are 2 electrons. In the L shell, there are 8 electrons. And in the M shell, KLM, M shell, there is only 1 electron. 2, 8, 1. First shell, K shell, 2 electrons. L shell, 8 electrons. And M shell, there is only 1 electron. And what about the nucleus? Let us draw the structure of the shell-wise structure of a sodium atom. See here, there is the nucleus. Atomic number is equal to 11. Since atomic number is equal to 11, what must be the charge of the nucleus? You know, for 1 proton, atomic number is number of proton. For 1 proton, plus 1 charge. Plus 1 charge. But here the atomic number is equal to 11. And therefore, there will be plus 11. That is the charge of the nucleus of the sodium atom. In sodium atom, since atomic number is equal to 11, atomic number is equal to 11, there are 11 protons. 1 proton plus 1 charge. So 11 protons plus 11 charge. So that is the charge of the nucleus. Now, you come to the K shell. In the K shell, there are 2 electrons. In the L shell, there are 8 electrons. And this you have studied in the 10th standard, the shell-wise arrangements of electrons. Now, you come to the M shell. This is K shell. This is L shell. M shell, there is 1 electron. This is our sodium atom, shell-wise arrangement. Now, you remove 1 electron from sodium atom. So, sodium atom minus 1 electron. Then what we get? We get Na plus ion. Na plus ion, positive ion, cation is formed. So, Na plus ion, the cation is formed by the loss of 1 electron from sodium atom. Removal of 1 electron from sodium atom. So, in sodium atom, how many electrons will be there? Say, in sodium atom, atomic number is equal to 11. Therefore, 2, 8, 1, that is the number of electrons. Now, Na plus, 1 electron is removed. So, there will be only 10 electrons. 10 electrons. So, in Na plus, there are 11 protons. 11 protons. No change for the nucleus. 11 protons. Therefore, plus 11 charge for the nucleus. But we have only 10 electrons. 10 electrons. 10 electrons. For 1 electron minus 1 charge. So for 10 electrons, minus 10 charge. Therefore, the resultant charge will be plus 1. That is why we get Na plus ion. See, Na plus ion. So, a unipositive ion is formed by the removal of 1 electron. A dipositive ion, plus 2 ion, is formed by the removal of 2 electrons. Tripositive ion, plus 3 ion, is formed by 3 electrons, like that. Okay. So, positive ion or cation is formed by the loss of electron or a removal of electron. Corresponding to the number of electrons lost, the number of positive charge also increases. For example, from sodium atom, if 1 electron is removed, we will get Na plus, and Na plus has only 10 electrons, but there are 11 protons in the nucleus. So the total positive charge of the nucleus is equal to plus 11, and the negative charge due to 10 electrons is equal to minus 10, and there will be a resultant positive charge for the ion. So Na plus ion is formed like this. Now, what happens to the size of the atom and the size of the ion? Size of the atom and the size of the cation, positive ion. See, in the positive ion, in the cation, the number of electrons will be less than the number of protons in the nucleus. The number of electrons will be less than the number of protons in the nucleus. So the attraction between the remaining electrons and the nucleus increases. Say, before the removal of electron, 11 protons or 11 positive charge attracts 11 electrons. 11 positive charge attracts 11 electrons. But after the removal of electron, 11 positive charge attracts only 10 electrons. So the attraction between the nucleus and the remaining number of electrons will be increased. And if the attraction is increased, what will happen to the size of the cation? What will happen to the size of the cation? The radius of the cation. The radius of the cation decreases. So in general, we can say the cation is smaller than, in general, cation is smaller than, positive ion is smaller than the corresponding parent atom. Smaller than the parent atom. Positive ion is smaller than the parent atom. I repeat. In the parent atom, the number of protons and the number of electrons will be the same. But in the cation, positive ion, electron is removed. So number of electrons will be decreased. But the nuclear charge remains the same. The effective nuclear charge increases. Say nuclear charge remains the same, means the same positive charge attracts lesser number of electrons, and therefore the size of the cation will be smaller than the corresponding parent atom. So in this case, the size of Na plus ion is less than the size or a radius of sodium atom. The radius of sodium ion, Na plus ion, is smaller than the radius of Na sodium atom. And that is about the size of the cation. Now you come to the size of the anion. You know, anion is a negative ion. Anion is a negative ion, and it is formed by the addition of an electron, gain of electron. For example, take chlorine atomic number 17, and the configuration will be 287. 1s2, 2s2, 2p6, 3s2, 3p5. So 287. So in the chlorine atom, protons is equal to 17, electrons is equal to 17, and what about the charge? Protons 17, so plus 17 charge, nucleus, and electrons 17, so minus 17 charge from electrons. So atom as a whole is electrically neutral. The number of protons is equal to number of electrons. So atom as a whole is electrically neutral. Now we are going to add an electron into the chlorine atom. Then what happens? Say chlorine 287. 287. Into this, we are going to add one electron. Then what we get? We get a negative ion, Cl minus ion. We are adding one more electron. So in the Cl minus ion, chloride ion, see the electronic configuration will be like this. One more electron is added into the outermost shell, or the so-called valence shell of a chlorine atom. So there will be 288. That is the configuration of the chloride ion. If it is so, you compare the size of a chlorine atom and a chloride ion. Anion. Here in the chloride ion, there are only 17 protons, atomic number 17. So 17 protons plus 17, that is the charge of the nucleus. And there are 18 electrons now, 18 electrons. So the negative charge due to 18 electrons will be minus 18, and therefore the resultant charge is equal to minus 1. That is why we have got a chloride ion, Cl minus ion. See? So a negative ion or anion is formed by the addition of electron. Now what happens? Say the number of electrons will be larger than the number of protons. In the anion, the number of electrons will be larger than the number of protons, and therefore the effective nuclear charge is less. The attraction between the outermost shell and the nucleus will be less compared to the parent atom, and therefore there is an expansion for the outermost shell and the anion size increases. So in general we can say an anion is larger than the parent atom. Larger than the parent atom. That is because when electron is added, the effective nuclear charge is decreased, attraction is decreased. And that not only that, there is an repulsion between the electrons in the outermost shell. So there is expansion for the outermost shell, and therefore the size of the anion increases. So in this case, we can say chloride ion is larger than the chlorine atom. Chloride ion is larger than the chlorine atom. So in general, we can say that cation is smaller than, cation, everybody has gone. So cation is smaller than the corresponding parent atom, while anion is larger than the corresponding parent atom. The rest we can see in the coming classes.